today we are going to be talking about inverse relations and functions, and this lesson can be kind of a doozy, so hopefully I'll be able to break it down for you so you can easily understand. I want to remind you that the difference between relations and functions is that in the case of a function, for every x value there's only one y value, and for a relation that's not necessarily the case. So and that's from back when we first did functions at the beginning of the year. But what I want to do right now is kind of talk to you a little bit about this idea of inverse functions. Inverse basically means to undo something. For example, you've already been exposed to inverses. You have done addition, and you know that to undo addition, you have to use subtraction. Well, subtraction is considered the inverse of addition. Also, you've done multiplication, and you know that if you want to undo multiplication, then you have to use division. So division is the inverse of multiplication and vice versa. So we have this idea of inverses. And right now what we're going to do is we've been talking about functions for a while now. And so the inverse of a function is basically another function, a different function, that basically undoes what the first function did. So first of all, if that's still kind of like you're confused, let me just try to break it down for you. Let's suppose that you have a function, and here I have a function f of x, and it's linear, so I'm going to start with a really easy function, 5x minus 3. Well, we know that we can treat the function kind of like a machine. A number goes into the function, hence the 2 here. And I'm going to do this 3 times for different values. But the 2 goes in, and something different is going to come out. But the idea is that you're putting the 2 into this machine, and the machine is taking your number, it's multiplying it by 5, which is 10, and then it's subtracting 3 from that. So in the end, you're going to get 7. So what if I put a negative 1 into the function? If I put a negative 1 into the function, I'm going to take negative 1, the machine's going to multiply it by 5, and then it's going to subtract 3. So if I multiply by 5, I'm going to get negative 5 minus 3, I'm going to get negative 8. All right? And then we have, let's just try a 3. So I put a 3 in here, and 5 times 3 is 15, and 15 minus 3 is 12. Okay? And you probably remember that the way that we use this information could be helpful for us for graphing. So you can even make a t-table, and that's kind of what I've started over here, is a little t-table. And I can put the different x values that I've used, and I'm going to put them in order. I didn't do that here, but I'm going to put them in order now. So negative 1 would come first. And when you put negative 1 into the function, out comes a negative 8. And that's basically the ordered pair, negative 1, negative 8, which you could plot later and graph. When I put in a 2, I get a 7. Now that's kind of crowded there, but hopefully you can see this is x is 2, y is 7. If I plug in a 3, then y is 12. So you get that. This is my t-table, if you will. Well, this is a function that's actually pretty easy to do. Not all functions are this easy. You can probably do some of this in your head. But I'm going to talk now about the inverse function. It's basically going to be a function that undoes all of what that function did. So what are the 2 things that this function did? It multiplied by 5, and it subtracted 3. So since we know that the inverse of subtraction is addition, you're going to see some addition here. Since we know that the inverse of multiplication is division, we see some division here, okay? But again, I want to start by plugging in what we know. So what I want you to see here is that if I put a 2 in the function, the 7 came out. So now if I want to undo everything, I'm going to take the 7 and put it into the undo machine, which is basically the inverse function. So I'll put a 7 here. And when I do that, I get 7 plus 3, which is 10. And 10 divided by 5 is 2. And voila, you can see how originally we put a 2 in the function, the 7 came out. If I put the 7 in the undo machine, then I get back to the 2 that I started with. See how that works? And we can do it again. In this case, I'm going to put in when I put in a -1, I got a -8. So now I'm going to put -8 into the undo machine. And -8 plus 3 is going to be -5, and -5 divided by +5 is -1, and I get my -1 back. So you can see that the -1 went into the regular function, a -8 came out of the regular function, and if I put that -8 into the inverse function, I get back to the -1 that I started with. So it kind of undoes everything. All right, last one here. We put in a 3, we got out of 12, so now I put in the 12, and I'm going to get 12 plus 3 is 15, and 15 divided by 5 is, again, 3. So again, we see that concept of 3 goes in, 12 comes out. When 12 goes in, the 3 comes back. So it's a matter of undoing what one machine did. Okay, and again, we can set up a t-table for ourselves over here. And we know that when we want to kind of keep the same order from before, we know that when we put a -8 in, a -1 comes out. We know that when we put in a 7, the 2 comes out. And we know that when we put in a 12, a 3 comes out. So now I want to kind of compare for you these two t-tables. You will look at them, you have -1, -8, and over here you have -8, -1. It appears that they've switched sides. 2, 7, 7, 2. 3, 12, 12, 3. If you can observe anything from this pattern, it's this, that the input of this machine is the output of the inverse machine. And the output of this machine is the input of the inverse machine. So basically, what we refer to as input can be better said, the input, which is the x, is otherwise known as the domain. What goes into the function. What comes out of the function, which we call the output, is referred to as the range. So another way of saying this is that the domain of the function is the range of the inverse function. The range of this function is the domain of the inverse function. They interchange roles, okay? So basically that's what we learn from this, okay? So now I want to show you, this is kind of like just showing you the algebra of it. It's kind of showing you how the graph thing works, the fact that you can interchange x and y. And now I want to show you what this looks like when you graph it. Okay? Again, they're the same two functions I started with earlier, and I want to graph them for you. And one of the other concepts that I should remind you of very quickly is that when you have addition and subtraction, they always produce the identity. Two inverses always produce identity. For example, if I have x plus 5, I can undo the plus 5 by subtracting it because they're inverses. And when I put the two inverses together, I'll get the x back by itself. It's basically x plus 0, which is just x. 0 is considered the additive identity because you can add 0 to anything and you can subtract 0 from anything and it leaves it the same. Okay? Another one is multiplication and division. And again, with multiplication and division, if I have an x and I multiply it by 10, then I can divide it by 10 and they'll cancel, and basically what happens is I get x times 1, which is just x. So again, multiplication and division are inverse operations, and when you put two inverses together, you always get the identity for that operation. The identity for multiplication is 1. We call it the multiplicative identity. Again, because when you multiply by 1 or divide by 1 to any number, it stays that number. So you get your x back, okay? So for that reason, it shouldn't be surprising to you that I have over here a graph, and what you're seeing is this red line going right down the middle. Y equals x. We talked about x and y and their roles in the previous slide. And so basically when you have inverse functions, the role of x and y is interchangeable. So it shouldn't be too surprising that we're saying here that basically y is equivalent to x. They have the same value, okay? So that line, when you graph y equals x, there you go, is basically our reflector, our mirror, if you will. And that'll make more sense when I graph this. We know how to graph linear functions. -3 is the y-intercept. Oops, that was not good. We have our eraser going on. Let's put that back. There we go. So here's our -3 for our y-intercept, and our slope is 5/1. So I'm going to go up 5, 1, 2, 3, 4, 5/1. And I'm going to connect my line, and you're going to see this line go like that. And if you want to keep it going, there we go. Okay? So there you see my line. Just a basic linear graph. What I've done on the right over here is, this is our g of x function. It's the same function I had earlier. And what I've done is so that I can use my linear functions here, I basically divided each term by 5. So this is the exact same thing, but this just looks more like what we're used to. So mx plus b. So I'm going to go ahead and use 3/5 as my y-intercept. So that means that I'm going to go to 3/5 is not quite 1. So here's 1. So 3/5 is probably 1, 2, 3, maybe somewhere around here. It's not going to be very accurate or exactly, but more or less. And then the slope is 1/5, which means I'm going to go up 1. So I'm going to go up maybe somewhere right here, that's about 1, up 1, and I'm going to go over 5. Okay, so here's 1, 2, 3, 4, and then maybe 5 is right about here. Okay, and then I am going to connect my two values, my two dots here. And there I go. Okay, and what you should be seeing, okay, now again, my graph is a little bit, it's not exact, but you kind of get the main idea of what I'm trying to show you here. And that is that these two lines, the blue one and this darkish brown one, are supposed to be mirror images. I said earlier that the line y equals, that's kind of like my reflector. When you look in the mirror, you see your image, okay? This is supposed to be a mirror image, okay? And it's a little off, but you get the main idea that it's just because my numbers, my graphs are not, human error, that part of it. But the more careful you are, if you have graph paper, the closer you can actually get to that. But when you have two inverse functions and you graph them, you should see this pattern. You should see that the two graphs will be like mirror images of each other. All right? So that means that if I graph something, just to give you another idea real quick, if I graph something, I'm going to go ahead and put y equals x there. Let's say that my graph looks like this. It means that the mirror image should look like that. They should be mirror images right along this line y equals x. Okay? And that's again because y equals x is what we call the identity function. And that's going to come back in this lesson a little bit later. Another way that we use the identity function, we said earlier that when you put two inverses together, you're supposed to get the identity. When you add and subtract the same number, you get 0. When you multiply and divide by the same number, you get 1. When you have a function and its inverse function together, you get x, because x is the identity function. Okay? So, now, to the examples. Here we go. So I wanted to show you this guy. F of g of x, what I was just talking about. I need to go back real quick, and we can remember that f of x is 5x minus 3. Oops, sorry. Didn't mean to go that way. 5x minus 3. So over here, we've done this before. This is what we were doing in the last lesson. We're doing composition. That's probably why it was important in the last lesson. And we know that f of x is 5x minus 3. So we can write that as g of 5x minus 3. And the g function, you'll remember, was x plus 3 divided by 5. x plus 3 divided by 5. Okay? So over here we're going to do x plus 3 divided by 5. And this one was 5x minus 3. Awesome. There we go. Okay, so what do I want to show you? I want to show you that when you do the composition, when you put the inverse function inside of the regular function, they're supposed to cancel out, basically. So what you're going to see is I'm going to replace the x, so I'm replacing g of x with what the function was, which is x plus 3 divided by 5, and then the f function, if you recall, was 5x minus 3, so in the place of x, I'm going to put the g function, which is x plus 3 over 5. So I am putting the g function inside of the f function. What's going to happen there is that the 5's are going to cancel, one on top, one on the bottom, and you're going to get x plus 3 minus 3, and then those 3's are going to equal 0 because they're inverses, and you get x. All right, so when you have the function and its inverse, and one's inside the other, it cancels, so to speak, and you get x back. Just like when you have plus 5 and minus 5, it cancels, and you get your x back. Just like when you times by 10, you divide by 10, it cancels, and you get your x back. So when you put the inverse function inside of the regular function, it cancels, and you get your x back. And just in case you're wondering, it doesn't matter which direction you go in. So you can tell you that in that case, the f, I put the g function inside of the f function. In this case, I'm going to go backwards to see if it makes any difference. I'm going to put the f function inside of the g function this time. All right? So the g function was x plus 3 divided by 5. So I'm putting the f function inside of it. So here I go. And now I'm just going to simplify that, and you will see that it will not matter which direction you go in, it's still going to be the same thing. So on the top, I get 5x minus 3 plus 3. But again, we know that the negative 3 and the positive 3, that's 0. So now I get 5x divided by 5. And since 5 divided by 5 is 1, we get x back. All right? So you can see, hopefully through all of this, I will just kind of recap it for you here, just in case you were, not sure what was going on there. First of all, at this point, we've pretty determined that this is my f function, it's my starter function. This is my inverse function. And for the record, we have a notation for inverse functions, so we can call it f inverse. It's like f to the negative 1 power almost, but it doesn't actually mean to the negative 1 power. It just, when you read it, you just say f inverse. So right now it's called g of x, but it's also the inverse of f, so we could also call it f inverse of x. All right? So we have a function, and now we have the inverse. We understand that when you put the input into the regular function, that it's actually the output of the inverse function. So where all the input values were negative 1, 2, 3, those are actually the output values of the inverse function. We understand that the range, the output of the normal function, becomes the input of the inverse function. So where the output here was negative 8, 7, and 12, the input of the inverse function is negative 8, 7, and 12, which basically tells us that the domain and range are interchanged between the two functions. And then we use that information. Because the x and y are interchanged, we have this identity function, y equals x, that when we graph the two functions, they are mirror images along this line, y equals x, which is the inverse function. And then, of course, that we can do composition of the two inverse functions, and when we do that, the functions cancel themselves out, and you're left with just x, because x is the identity function. So now what I want to show you is how to apply this so that you can do your homework, obviously. That's the goal, right? So here's the first example. Find the inverse relation S. And this is probably the easiest part. It's very simple. What we're going to do is, because of the first thing that we said, we know that you can interchange x and y. The domain of one function is the range of the other. So basically, if I wanted to put my answer here, for my inverse function, all right, I would basically interchange x and y. So if x is negative 1, 0, 1, 1, it's going to be negative 1, 0, 1, 1. Ta-da! So the y values are 1, 2, 3, 4. Well, those will become the x values, 1, 2, 3, 4. And that's about as hard as that gets. You just interchange x and y for the inverse of a table like that, okay? Now it says to graph S and its inverse. So they want me to graph both of them, okay? So I've already put a little chart over here, and so we're going to start graphing that. I'm going to graph this one first, and we'll do it in the color of which it's, this is the regular function. So I'm going to plot negative 1, 1. Here's negative 1, 1. And that's, negative 1, 1. And then we have 0, 2. And then we have 1, 3. And then we have 1 and 4. Okay? Now, I'm going to take and graph or plot. Now, by the way, when you have a table like this, you don't have to connect the dots. That's just your graph. There you can kind of see it kind of looks linear, but then it's like, all weird. Like, don't connect the dots. But now I'm going to graph the inverse function. So now it's going to be x is positive 1, y is negative 1. And then we're going to get 2, 0. And then we're going to get 3, 1. I'm going to keep going here. Sorry about that. We kind of run out of some space there. So we're going to do 3, 1. So here's 3 and 1. And then 4 and 1. Okay? And now, just for the sake of you watching how this is reflected, I am going to draw in y equals x. 1, 1, 2, 2. Okay, these are my y equals x. Oops. Y equals x function, okay? So what you should be seeing is like this mirror image between those guys, these guys, these guys, and these guys. You can even, if I try to trace this just loosely, kind of like that, this graph is doing the opposite kind of thing like that, reflected. Now the only reason why it's not exactly the right way is because you can tell that the distance between my values on the y-axis is a lot smaller than the distance between my values on the x-axis. So this is a lot wider, and because of that, the graph looks like it's a little off. But again, if you had a graph paper, you wouldn't see that happen. So when you graph the function and its inverse, you're supposed to see how it's a mirror image along y equals x. So that is example 1. So you can try this one. Again, it wants you to find the inverse relation and then graph both the function and its inverse together. All right, example 2 is kind of like the same thing, but now we're not using a table, we're using an actual equation. So find the inverse of each function and then determine if the inverse is a function or not. That's a tricky little question right there. But the way that we do this, the way that you determine whether or not the inverse or not, the way that you find the inverse goes back to that whole interchanging domain and range, interchanging x and y. The first step that you use when you are interchanging or when you are finding the inverse is to interchange the variables x and y. So instead of writing y equals x squared, I write x equals y squared plus 3. Now again, the reason why it's okay to do that is because with inverse functions, the x and y are interchangeable. That's not always the case, but it is the case with inverse functions. So because of that, I interchange x and y, and then I proceed by solving for y. So I subtract 3 from both sides, so I get x minus 3 equals y squared, and then I square root, and we've already said this before in class, anytime you square root something, you have to put plus or minus. So you get plus or minus square root of x minus 3 for A. For part B, find the inverse, same idea, you want to interchange x and y, so x equals 3y minus 10, and then solve for y. So I'm going to add 10, so I get x plus 10 equals 3y, divide by 3, divide by 3, so y equals x plus 10 divided by 3. Okay, so since this function is y, you can even put y inverse. Y inverse is, in this case, x plus 10 divided by 3. In that case, the square root of x minus 3. Now, the second part of the question is the inverse a function. Now that I know that this is the inverse, the question is it a function? And that goes back to what I said earlier. You're only a function if for every x value, there's only one y value. Well, a quick way of knowing that is by looking at the equations, okay? Basically, if I choose any random x value, like let's say that I just chose x equal to 4, okay? If x equals 4, what will the y value equal? So ideally when I do this, I'm only supposed to get one value for y. For every x, there should only be one value for y. So when I plug in the x to this equation, I'm going to get plus or minus the square root of 4 minus 3. Okay? And what is 4 minus 3? 1. So that's going to be plus or minus the square root of 1, which is plus or minus 1. So when I ask you how many y values are possible when x is 4, the answer is 2. When x is 4, I can get positive 1 or I can get negative 1. Well, because of that, this is not a function. It is the inverse, but it's not a function. Okay? A function is when you put in an x value, you can only get one y value. And by the way, a really huge hint to that, if you don't have to plug in the numbers to understand this, all you have to look at is this plus or minus. The whole point of saying plus or minus means that there's two options, a plus or a minus. So because of those two options, every time you put in a x value, with the exception of the number 3, because with 3 you only get 0, will be your only y value will be 0 when you put 3 in. But for every other number, when you plug it in, you're going to get two answers, a plus and a minus. So that's not going to be a function. Now, in this case, this is a function for the same reason or for the opposite reason that that one wasn't. In this case, when I plug in 4, I get 4 plus 10 is 14. 14 over 3 is 14 thirds. There's only one y value. There's no plus or minus in front of the x plus 10 divided by 3. So this is a function and a is not a function. So that is how you answer those questions. So here's one for you to try. There's 3 here. There's a linear one and a couple of quadratics. So there you go. Remember to just interchange x and y and then proceed to solve for the y value when you're finding the inverse. Okay, so now we have, by the way, I don't know if you noticed this, but these are the exact same functions from before. So in this example, we had the same x squared plus 3, 3x minus 10. And the reason why I bring that to your attention is because they're asking me to graph the relation and its inverse. So what I want to do right now is bring up the inverse function. I don't have to do it all over again because I already know from earlier that that was the inverse function. Okay? This is information that I'm recalling from over here. We already found the inverse of those functions. It was plus or minus the square root of x minus 3 and x plus 10 divided by 3. So that is what I'm using here. Okay? But they want us to graph them both. So again, I'm going to try to make my graph a little bit better this time. And not, hopefully it won't come out all crooked like. But x squared plus 3, you will recall that when you graph a parabola, like this one, it's basically a parabola shifted 3 units up. So here's 1, 2, 3. And it's x squared, so if x is 1, I get 1 squared is 1, and 1 plus 3 is 4. So I'm plotting the point 1, 1, 2, 3, 4. Okay, so I've got this guy. And when x is negative 1, it'll be positive 4 as well. So there's my graph. Okay? And then when I graph the square root, the plus or minus here, there's a couple of things that you can do. If you don't know how to graph the square root, which is totally okay, you can use your t-table. Okay? For example, what I did is I know that when x is 0, the y value is positive 3. When x was positive